Okay, so today we will start off with a look at the question paper what you had for the exam and the answers. As I said some time back, there is not much to discuss for you because the questions were very straightforward and you have answered fairly well, but for the sake of this lecture we will do that. So of course this question there is not really many people who haven't answered it. Like lines plan, you are basically expected to write some definition of lines plan, that it has and write that you have these three, mainly that it has three views, the all the profile, plan and body plan. So and if you can just draw a small figure, something which looks like that, that's more or less enough. Then prismatic coefficient, I forgot the exact definition. It's the ratio of, what are the two? It's the ratio of volume to something, no, delta, what is it? Midship area to length in, no, breadth into draft, length into draft probably, then length into breadth probably, most likely. I have to check again, I forgot. Anyway, that
volume upon midship coefficient into length.
midship coefficient, okay. Yeah, that is very straightforward definition only, is prismatic coefficient. Then some people have not written LCF, longitudinal center of flotation. That seemed little more, a lot of people have left that. So LCF is, you know what is it? Is the centroid of the water plane area. That is all you have to write really. That if you have written a lot of things and not that, then doesn't make any sense. So it is the centroid of the water plane area, that is, or the longitudinal position of the centroid of the centroid of the water plane area. So that is Archimedes principle is very straightforward. Downward weight is equal to upward weight, or weight displaced is equal to the weight of the floating body, something like that. That is okay. Writing arm is also okay. We have writing arm is basically GZ. So if you know that, then you can draw the GZ curve, that is all right. MCT is the moment to change the trim by either 1 centimeter or by 1 inch, whichever you write is okay. That also many people have left, that they have not written that. Then barycentric axis, what is it? It is the axis through the center of flotation, transverse axis through the center of flotation. So that is enough, that one sentence would have been enough. Then trapezoidal rule, you just write it is to sum of the areas, and I think it is 1 4 4 1, right? 1 2 1 2 4 2, right, like that, right, 1 2 4 2. So okay, that is also okay, that is the trapezoidal rule. Then so that is, this is okay. This is also very straightforward only, but there is, the second part of it, like you the first, of course, you have to explain what is the static, that curve should be there, otherwise there is no point in this explanation, in this question. So what you have to do is to draw that curve, and of course in that curve you have to mention that the tangent, and that description should be there, okay, that when you at 1 radians, if you draw a vertical, that is equal to GM, that definition should be there, and then same thing you have to draw, that's all. And I am not going to exactly measure if it is a tangent or anything, but it should look like a tangent, at the origin it should look like a tangent. So that is the important thing. Some people have drawn some strange things, but mostly 90%, 95% have drawn okay. Okay, so this is all right. I guess this is a little, it's not at all complicated, but some mistakes are there. If you want, I will just explain this. 108. Okay, so the question is that so you are told that the weight of the vessel is given. There are 2 or 3 slight confusions in this problem. Okay, one thing, I myself made a confusion in the exam, because I told some people that it is given 14,000 tons is the weight of the ship. Now many people ask me, is it the weight of the ship plus water, or is it the weight of the ship is the without water, like that. So I told differently, I think, to some people. Actually it is the weight of the ship plus water. So but since I told like that, both I have given full marks, it does not matter whichever way you take. So, but really speaking in the problem, if you think itself, it is said that the ship has water in it and the total weight is 14,000 tons. So, obviously, it is the weight of the ship plus water. Any rate, it does not matter. So, the question is, so it is like this, you have a ship, so here you are having a fluid and this fluid is transferred from the left side to the right side of the ship. It is listed in some angle initially and so you have to find the final list. So, the first thing you have to find is the, as I told you before, someone asked me a very valid question. It's said that the tank is fully filled. Where is it? Is full of fresh water. That is actually a good point. The problem is defined like that. It from the book also it's defined like that. That is that it's actually not. If it is full of fresh water, there is no free surface effect. But let's assume something. It means it's not full. It's slightly means the tank is slightly bigger. So there is free surface effect. So that is the problem is a free surface effect problem. Okay. So we have to consider that. So so first of all, you have to find the free surface effect or free surface moment. So you will have to do I into rho of fresh water, that is this the free surface moment. I mean I do not think I will do the derivation or anything, you will just write the final expressions. So this becomes like LB cube by 12 into density of water is 1000 or 1 ton, in tons meter it will become so many ton meter it will become. So that you have to do, this is the first thing. Then then what you have to do is make the table and you have to find the shift in G. So first of all, what should you calculate? You have to find the weight of water transferred, first thing, volume into rho, that and all you can very easily calculate. Then shift in the center of gravity is G0 G1 is equal to initial G0. Okay. So initial G0 G1 is said to be initial tan theta, or theta is said to be 3 degrees, it is listed 3 degrees to port. So tan 3 degrees into Gm, is Gm given? Kg and Km are given, right. So you can find Gm. Okay. So G0 G1 you find, okay, that is your initial G0 G1. So that you have to find, that you should have got it as 1 tan 3, that you will get 0.054. Then what this is one important part of it, that is weight. You have to find two things, first Kg, okay, then moment of that weight about and multiplied with Kg, that is the weight multiplied with Kg, that moment. Then you have to find also this horizontal moment, which is basically the free surface moment, okay, that will come there. Only thing in that is one slight thing, that is if you are finding the Kg for the water transferred, that most people have done differently, that wrongly in fact, that is left side note, see that this is the water, right. So water is removed from here, not from here. So almost everybody has taken Cg of the water removed to be at 0.25, this is 0.5, this is 1. So everybody has taken it to be at 0.25, that is Cg of the water, or at 0.5, either way, means this water is removed, right. What are you doing? You are subtracting one water removed, adding one water added, okay. When you are removing the water, where is the center of gravity of the water removed? It is at actually 0.75, not at 0.25, is it clear, right. It is not at, means you are not removing water from the bottom, you cannot do that. So you are removing water from the top and it is transferred here. So it is not at 0.25 actually, it is at 0.75. So that that is a mistake in almost all papers except for very few. Okay. So, that is one thing. Then of course, you have to find, then other things are okay, that is free surface moment. Then you find the moment port, moment starboard, you find the net G0, G1. Then other than that, there is nothing in it. So, what did you in general get as answer, most of you, final list? Do you remember? You do not remember, okay. Anyway, you should get it as almost 1.5 or 1.6 degrees, at least close it should be. That 0.75 mistake is there with most, still you will get some 2 or 3 degrees you should get, I think. Should not be getting very strange answers like 10, 20 degrees and all. If you get, you have something really wrong. Okay. Anyway, all right, it's not tough at all. I don't think that's anything. The only one problem is that it's basically a free surface effect problem. You just have to know how to apply it. Then this is the problem. One more problem is that in this I told you, that is one of the important things you have to see here is that it is a box shaped vessel. That is the important thing. Means if you try to use the usual formulas, that is like GM, using GM, kg and all that, you won't be able to solve it. That is why that box shaped vessel is there. Box shaped vessel, you I have already done a set of formulas where that is these things like Km is equal to d by 2 plus I think, is it Km or K? I think it is Km only. Km is equal to d by 2 plus I by something. B square by 12 d, right? Yeah. So, Km is equal to d by 2 plus b square by 12 d. This formula actually, that is all. If you know this formula, the problem is very just straightforward. There is just substitution. So, you do Km is equal to this, and you know that for the vessel to be stable, Km should be greater than Kg. You put that condition and then you solve for it. You should get should be less than 0.211 or it should be greater than, draft should be less than 0.211 or draft should be greater than 0.789. So, that is the answer, and the other answer is, though some people have asked me also, it is a little weird, you get GM as negative, you are asked the minimum GM, but no, it is the minimum GM, okay. It is not the optimal GM or the operating GM or it is the minimum GM, therefore, it is okay. So, you get minus 0.092 is the minimum GM. Anyway, from differentiation you can get only the minimum or the maximum. So, that is why that is asked. So, that is the second part of that problem. So, the only thing here is you should know this, Km is equal to d by 2 plus b square by 12 d. Once you know that, then it is very straightforward, there is nothing in it. Okay. All right, that is all for the exam. Okay, now we go into a it is mostly continuation only. What are known as something known as Kn curves. It is not, of course, not nowhere as important as the statical stability curve or the cross curves of stability or anything, but still it is used. So, we will discuss it. It is known as the Kn curves. The thing is, it's you use the Kn curves to find out the GZ curve of the vessel. So, in that way it is important. So, Kn from Kn curves, once you have designed the ship, you can use Kn curves. What I will tell you what it is. Kn curves, you can use it to get the GZ curves, and of course, GZ curves are the most important. That writing arm curve and the statical stability curve is the most important in this course itself. So, and we use a simple definition of a kind of ship we call wall sided ships. It just means straight, okay, the sides are straight, they are called wall sided ships. Of course, everything we have defined so far, all the derivations I have done so far is all for wall sided ship. I have never defined anything for, so it does not matter, but for the, you should know what is a wall sided ship. That is, you, because in general you will see that ship is not like this, it is very rarely like this, it is like this, okay. It will have some bulging, there is always it will come like this or a little bit. So, none of that is considered in wall sided ship because it is for mathematics, it is all for straight lines. Okay. So, consider this ship, consider this okay, these are two parallel lines, G z is a perpendicular to that line. So, this is a writing arm. So, here somewhere you have b theta, so or b phi. So, the initially you had the ship in an upright condition, something caused it to heel, and as a result it has moved into the new position b phi, and we have drawn the vertical there, and G z is the writing arm. So, the weight W is acting here upwards. Now, this is K, okay. This is the keel, the bottommost point of the ship is the keel. Now, to this line, if you draw a vertical, I mean a perpendicular like this point we call it as N, okay. This point, it is not b phi, b phi is somewhere up here, let us say this is b phi is up there and G z is there, and so we see that K n is parallel to G z, both of them are perpendicular to that vertical through b phi, okay. So, this K n which is drawn as a perpendicular to this vertical at b phi is known as the, is what we are calling as K n here, K n curve, and as phi keeps changing, means this is phi, as phi keeps changing, you know that b phi will keep going upwards, and similarly the n, as also you can see, will keep going outwards. So, K will be fixed, K is the keel of the ship. Now, this curve which this, because of the movement of n, that curve that is traced out by n is known as the K n curve. So, this is what we call as the K n curve. Now, just a little bit of G z is equal to, let us call this point x, K n minus k x, right. G z is equal to K n minus k x, and k x from this you can see directly is equal to k g sin phi. From the figure you can see that k g sin phi. Therefore, G z is equal to K n minus k g sin phi. Now, that is what I said. So, first we use this K n curve to find the G z curve. So, that is the purpose of the K n curve. K n curve, there is way of finding a K m curve for a particular ship, and once you have the K n, using this formula, that is K n minus k g sin phi. Of course, we need to know the k g of the ship, and once you know the k g of the ship for different angles of phi, means you start from phi 10, 15 like that, you keep increasing phi, and as phi keeps increasing, you find the different values of g z, and once you have the different g z's, you can draw the g z curve. So, this is the purpose of the k n curve. So, and this is the formula used for calculating the g z from the k n curve. Okay, for instance, we will see this problem. Now, they are saying there is a ship that weighs, that has a displacement of 26,000 tons, and its kg is equal to 9.6 meter, and km is equal to 11.9 meter. Now, you are given the kn table. Now, you are asked, does this ship comply with the load line regulations? That means, especially for the end semester, you have to remember these load line regulations. That is, the load line regulations you have to remember. This is the most important part. There are a lot of them. For grains I have set some. So, if you have to do the problem, to do one problem itself will take you definitely half an hour to 45 minutes, it is that kind of problem, and if you do not know the regulations, then you cannot. So, this is the most important one is that you should know that the area under the g z curve, I will just write the most important of it. So, area under the g z curve should not be, it should be greater than or equal to 0.055 meter radians up to an angle of 30 degrees, up to phi equal to 30 degrees. Okay. This is the first rule, that is the area under the g z curve should be greater than or equal to 0.055 meter radians up to 30 degrees. This is very important, and in fact, there are three more very important ones. Then it should be greater than or equal to 0.09 meter radians up to 40 degrees. Okay. This also is very important. Then third one is that between 30 to 40 degrees, you should have an area of 0.03 meter radians. Okay. These are three rules that you definitely have to remember. I think you should remember it always. It's very useful. I mean, like interview and all, they will ask something. Load line regulations are very common. There are of course many specifications. This keeps changing. For this is general, which can be applied mostly for all ships, but when you specify, for example, for each type of ship it differs. We have seen for grains it's different. We mentioned a couple of different rules. It's not different, but it's slightly more modified. Okay, for different ships. Similarly, for container ships there are slightly different rules like that. But this, even if you do not know any of them, at least if you remember this, you have something to say. Okay, you are not far off from the mark, you can say something. So, this better remember. So, these are the, if you do not know any, means if you do not know anything else, just use these rules. This is okay for all the ships. Even if you do not know the remember the grains, at least if you apply this, you have something. Okay. So, your question is that does this ship comply with the load line regulations? Okay. So, you will be given the problem like this. So, that is, you will be given heel and kn, means heel 0, kn 0, just like that problem I gave you the g z, just like that 1.05, like this 12, 2.67. Okay, like this you will have the till 90, you will have 7.63. So, you are given the kn table, instead of giving you the g z table, now you will be given the kn table, from which you have to find the g z. So, what you do is, first thing you have to do is you make the first table, first one more line here, you put kg sin phi. You have to know kg, of course, it's given 9.6, it's given. So, kg sin phi, for each of these phi's you find the kg and put it here. Okay. Then you do kn minus kg sin phi gz is equal to kn minus kg sin phi, you put that here. This is your, so this set of tables you have to make. This gives you your final gz curve anyway. Then you are given km is equal to 11.9, then kg is equal to 9.6. Therefore, you find gm, km minus kg 2.3. Actually, I think there is a rule regarding gm also. Gm should be gm should be greater than 0.15 meter, that is also important. Now, so first of all, first rule you can check that gm is 2.3, it's definitely much better than the minimum gm, that is all right. Then you have to check the other rules, does it satisfy the load line regulation. So, you have to find the area. So, that is like this only, heel gz, you write the Simpson's multiplier, then function of area, um, 0, 10, 20, 30. So, you find the area up to 30 degrees. You have to in fact to do two things, you have to find the area up to 30 degrees, then you have to find the area up to 40 degrees, and you have to find the area between 30 and 40 degrees, both, or three things. Okay, all three things you have to find. So, first you do this, gz is given, you put that, then Simpson's multiplier, you can you can use any of the Simpson's multipliers, and or you can use a trapezoidal rule or anything, and then you find, so you put that here, then the function of area, multiplication of this, summation, and then finally the rule. Okay, here they have used a 1 3 3 1, there is a like this, and so 5 12, actually 0 5 12 15 30. So, 30 is not a problem, but 40 is not there. 30 to next one is 45. Let me see how they have done. So, till 30 there is no problem. Oh, okay. You have to do some, the only way when you are given a problem like this is you have to draw the gz curve. So, you have to do some kind of approximation. What they have done here is you take up to 30, that is no problem here. From 30 to 40 you have to draw some kind of, make some kind of parallelogram, make some kind of rectangle, okay, and make an assumption like that. So, that is what they have done here. They have made a rectangle and roughly said this must be the area and subtracted that from 45. That is all right. And so, at any rate you have to be ready to draw the gz curve. Then, so similarly, you do this from 30 degrees, then next one you have to do till 40 degrees, you have to find the area. Then, so once you have that, you have to find the area between 30 to 40. So, now each of those you check, area up to 30 degrees you find, you see if it satisfies the regulations, if in this case it does. Similarly, 40 it satisfies, between 30 and 40 it satisfies. So, three things you have to check. So, if all three are satisfied, then the problem is correct, I mean the ship is okay, all right. Okay, then let us look at some effects of wall sided vessels. this is a okay, this has a G here, and it is now healed by an angle theta of phi. Then now from this G I draw a vertical to this Z. Now, we can do in this problem we do it in a slightly different form, that is initially it is at B and then it moves to B phi. Okay, let us say it is here. Now, let us split this. It goes means let us assume that the healing is done in two steps, one like this and then like this, means it healing can be anyway, healing is we cannot change, healing happens. Let us assume that the movement of B is like this, B moves horizontally and then vertically, okay, or rather the total movement you split it into horizontal and movement vertical, you just split it like this. Now, here we will draw like here I draw a vertical and you get B phi. Now, I will call this B, this I will call B 1 and this I will call B 2. From here I draw a perpendicular. Okay. Note that this perpendicular will be parallel to this G z. Similarly, G z also will have a component like this, let us call this point x, the intersection with the other line is x. Now, as you can see, G x will be due to the movement of B to B 1, okay, and the movement from x to z will be due to the movement from B 1 to B 2. That is, all we have done is in totality what has happened is B has moved to B 2, okay, that is the new position of B phi is B 2. Therefore, B has moved to B 2 and it has moved like this, B has moved to B 1 first and from B 1 it has moved to B 2. B 1 is a horizontal movement and B 2 is a purely vertical movement. Okay. So, B phi is just a general term, I mean I use it to yes, B 2 is the final B phi, yes, B 2 is the final final B, yes. Then therefore, you have this G z, note that this we are calling it as y, okay, this point is y, okay. So, this is y, so you have B 2 y, B 2 y will be a line which is parallel to G z, because both of them are perpendicular to this line, okay, because this line which I have tick marked is parallel to this line, okay. These two lines are parallel, it is drawn like that, I am drawing it like that. So, okay, now we need this figure, okay. Now, G z is equal to G z is equal to G x plus x z, okay, it is straightforward from that, G z is equal to G x plus x z. Then now, note we are doing similar thing, couple of things we have done many times. So, I will not repeat that, that is we have done that there is a shift of wedge from one side to another, we have talked about that, the movement of one volume to another side, and we have also talked about the coordinates of the center of that volume, or which we can call it center of buoyancy or the center of gravity of that volume. So, that is we have said it is, if this distance is b, this is b, okay, the whole thing is b, therefore, this is b by 2. Now, its center of gravity will be here, which is b by 2, this will be 2b by 3, 2 by 3 of b by 2, okay, that will be this distance, okay, that those things we have said. So, this is your, so there will be similarly there is a height here which will be, note that this height will be, if this is b by 2, this will be b by 2 tan phi, okay. So, this is equal to b by 2 tan phi, b by 2 tan phi, okay, all right. Then I am just writing the dimensions because there is no need to repeat it. So, here there will be a b by 2 tan phi, this is b by 2, and the center of gravity is, therefore, to find, there are a couple of things we need to find. For instance, you will need to find the volume of the wedge that has transferred, which we write it as half base into altitude into length. So, half base into altitude is, this is the base, half base, either way half base into altitude, okay. So, it will be, base will be b by 2 and your altitude will be b by 2 tan phi, okay. So, half of that will be give you your area into volume into length will give you the volume, that will give you the volume. Then another thing we need is G0 G1, means we have to find the distance through which the, here you have a center of gravity somewhere, this center of gravity is shifted to here. So, we have to find the shift in the center of gravity of that wedge, this also we have done many times, that shift, this, for that you need this distance is 2 by 3 b by 2, which is b by 3 twice that 2 b by 3, okay. So, that is the distance through which G of the volume has shifted. So, once you know these two things, I will just write the expressions, that is, you will have the shift in the center of gravity of the center of buoyancy of the whole ship, not for the volume wedge alone, for the whole ship, the shift in b 0 b 1 is given by V is the volume of the wedge into G 0 G 1, let us assume to be the shift in the okay, I will explain. So, what do we have here? We have here a volume or which we called as a wedge is shifting from one side to another side, that is from one point it is moved to another point in the whole ship. Because, so, there is a shift in the b of the b of that wedge itself, and because of this movement of the wedge there is a shift in the b of the ship itself. There are two things, one is the wedge itself which is shifting from one side to another, there is a movement, because of its movement that volume which is contained inside the ship, that b of the ship itself shifts. We know that if a mass inside a whole big mass moves, a mass of that small mass will move by a distance x, the g of that whole big mass also moves by some distance. So, that is what this is, b 0 b 1 is that of the ship is given by v into g 0 g 1 of that small wedge, distance through which the center of gravity of the wedge, center of gravity or center of buoyancy, it is the same, I am not differentiating here, center of gravity of the wedge shifts divided by delta of the ship, okay. H means horizontal, we are talking about the first, remember I told you that the whole movement of b like this I have shifted into a horizontal plus a vertical. Let us consider the first thing alone, which is a horizontal shift, which, so we are finding b 0 b 1, the total horizontal movement of the whole ship, that is equal to, now this is the volume of the wedge. Now, I will just write this, remember it is half base into altitude, then you have to multiply with a dl. This dl is, remember you are finding the volume, dl is integrated, okay, small length, it is integrated over the whole length of the ship, you will get the total total value dl into 2 by 3 into b by 2 into 2. Yeah, actually there is a b by one more b by 2, yes. Actually, there is a mistake in the book also, there is one more b by 2, because finally it becomes b cube. Anyway, there is a b, yes, half base into altitude. So, yeah, it is half b by 2 into b by 2 into tan phi into dl, that is correct, that is half base into altitude into 2 by 3 into this thing. Okay. So, this will be your that v into this is equal to tan theta into or tan phi into integral 0 to L, which is the total length of the ship, b cube into dl by 12, it will come like this, okay, which is actually equal to your I tan phi. Now, what does it tell you? Therefore, B 0 B 1 is this divided by this V into this. So, I by del tan phi. Now, you know that I by del is equal to B m. So, it is equal to B 0 m or B m 0 B 0 m tan phi. Okay. So, this is the first relationship you are getting B 0 B 1, which is the horizontal shift in the position of B is B 0 m tan phi. Okay. Then now, from this we look at this figure again. What we just got is that B 0 B 1, okay, this distance B 0 B 1 is equal to B 0 m tan phi. This is B 0. So, B 0 B 1 is equal to B 0 m tan phi. Note, so directly what will you get? That will directly give you this is m. Okay. What actually we are doing here is, till now we have derived some expressions. For instance, we derived an expression that G z is equal to G m tan sin phi. We have already derived that. It is a very basic expression. I mean, we have done that many times. Now, what we are doing is, we are in this derivation we are actually giving it a small correction, means it is not exactly G 0, everything is slightly different, means G z is not G 0 m sin phi. What you will get it as, it will become something like G 0 m sin phi plus half B 0 m tan square phi sin phi. It becomes a little more complicated expression. This is the real expression, and to first order the other one is okay. So, it does not matter, means whatever you are using, you are mostly going to use only the other one. Only for this purpose of this course, I think you will be using this. Very rarely will you go into the other one, into this one. You will be using mostly when you are doing any kind of calculation, you are going to use only G z is equal to G 0 m sin phi. That is a very common expression, but we are doing the first correction, and this is the real expression. I mean, for this course you have to know this. So, all right. So, you get that this is m. Okay. So, this is the correction we are adding. So, from this you can get one more thing from the same figure. You get that G x is equal to G m sin phi. G x is note that we have actually, what did we get till now? We have already always defined that G m sin phi is actually G z, means this thing G z. So, we see that when you really cut it down, when you keep going deeper and deeper, it is not really G m sin phi is not really G z, but according to this it is only G x. Because, and I will explain one more thing. For instance, if you how do we say, means we initially say ship is initially in the upright condition, then we tilt the ship a little. What happens when you tilt the ship a little? B goes to B phi, and how did we define at B phi? If you draw a perpendicular or a vertical, where it hits the initial vertical, you get m. You see, it is not exactly true here. It is this which hits m, but you have to notice one more thing. If you draw look at the figure itself, the distance is so small, it is almost 0. Okay, there is for this for the purpose of this derivation, it is important. What I am trying to say is that, for instance, in a viva or something, if someone asks you know, what is anything related to this, you do not need to go into this thing, because it is not really relevant in that sense. In a general sense, it is not relevant. So, you do the previous thing only, but this is just a very detailed calculation. Okay. In reality, this is correct, but it does not matter, you use the other one always. For the exam only you use this. So, the thing is, when we always say, you will never hear anywhere in naval architecture, that is, when you draw a vertical at B phi, when you draw it where it hits the original vertical, that is called as m. It should have been here actually. So, it is not there, but it is actually here. It is actually only the horizontal movement of B that matters in the movement of m. Okay. So, in the movement of, or in the position of m, the only thing that really matters is the horizontal movement of B, but when it shifts, the vertical movement of B in fact is so small compared to the horizontal movement, we never bother about it, that is all. But you should know this. So, that you get Gx is equal to Gm sin phi, that is one detailed expression. Now, next what do you have? You have the vertical shift in. So, first we moved from B0 to B1, now it will move from B1 to B2. Okay. Now, we are moving it like that. Let us consider the vertical shift. Okay. So, that is vertical shift is B1 B2, it will be given by V into G0 G1 vertical divided by delta. So, the expression is same, the formula is the same, V is the volume of the wedge, this thing. So, this G0 G1 that I am talking about, small G0 G1, this one, this G0 G1 that I keep writing here is this. Okay, this is G0 and this is G1, all right. So, I am talking about this G0 G1, it is a shift in the center of gravity, center of either of those, center of gravity of the wedge or the center of volume of the wedge, either way you can look at it. So, the volume, this volume, one volume goes in, one volume comes out. So, this volume goes in, this volume comes out, as a result of which this wedge is coming out, this wedge is going in, again as a result of which one volume is, it is like one volume shifted from one side to another side. So, G0 gets shifted to G1, in fact it will be here, not here, it will be here actually, sorry, G1 will be here and this G1 will be, G0 will be somewhere here. Okay. This is just the horizontal component of it, this is the horizontal component of. So, in the previous case I wrote G0 G1 horizontal, which is actually this distance, and now we are talking about the vertical shift in G0, that is G0 G1 vertical. So, this distance means, so this distance is what I am calling as G0 G1, G0 G1 vertical. Okay. This is the vertical movement of G0 G1. All right, then. So, the because of the shift of this wedge from G0 to G1, the center of gravity of the ship itself will shift, or the center of buoyancy of the ship itself will shift, means because of the transfer of volume from one side to another, from in a vertical direction, not from one side to another, in a vertical direction also G is moving. So, when this volumes center of volume or the center of gravity shifts from this point to another height, the whole center of buoyancy of the ship itself will shift from a lower to a higher point. So, that is what this is. So, B1 B2 is equal to V into G0 G1 vertical divided by del sorry, then and this one vertical will be given by, again same thing, half base into altitude. So, half base into altitude, this is the same thing, into dl into note it will be either 1 by 3 from the bottom or 2 by 3 from the top, either way you are looking at it, 1 by 3 into b by 2 tan phi into 2, because one is there at the top, one is there at the bottom, same thing, the same distance. So, this becomes tan square phi by 2 integral 0 to L b cube dl by 12. Okay. Then this is equal to tan square phi by 2 into I, where b cube dl by 12 we know is the moment of inertia. Therefore, B1 B2, which is the vertical shift in the center of buoyancy of the whole ship is given by half I by del tan square phi. I half I by del tan square phi. Yeah, which is equal to half B0 m tan square phi I by del is written as B0 m. So, B0 m tan square phi. So, this this is your final expression B for B1 B2. Now, let us look at that figure again. B2 okay. Now, B2y, we need one more thing to complete this derivation, that is we need to get B2y, I will tell you which is y. In this figure it is given, that is from this B2 I have drawn a perpendicular to this line which is actually y. So, B2y, therefore, that B2y is given by is equal to B1 B2 sin phi. Let us look, I think it is correct, B1 B2 B1 B2 sin phi. Okay, you look at this triangle, this small triangle here which I have darkened. In that triangle you have B1, a triangle made with B1 B2 and y. So, you have this one triangle. So, in that you will get B2y is equal to B1 B2 sin phi, B2y is equal to that, which is equal to half B0 m tan square phi into sin phi. Now, again note that B2y is the perpendicular distance between this line and this line. They are two parallel lines. It is the same as xz. Xz is also the perpendicular distance between the two parallel lines. It is the same thing. So, this is equal to xz. All right. Okay. Now, we have split gz into gx plus xz. Now, xz is given by this, given here. Gx we derive from our horizontal movement somewhere there, here, Gx is equal to Gm sin phi. Okay. So, two expressions we have got for Gx and Gz, as a result of which Gz becomes sin phi into Gm plus half B0 m tan square phi. Now, note our earlier derivation said that Gz is equal to Gm sin phi, which now says is equal to Gz is equal to sin phi into a little more things. Now, if you do the calculation, you will see that these things are very small. Okay, B0 m itself, Bm itself is a small quantity. Now, you will see multiplied by tan square phi, we usually have phi very small, therefore, phi itself is small and tan square phi is very small. Now, it is again multiplied by sin phi, which is also small. So, it is a second order, it is a very small order quantity, it does not really matter, but this is the real expression for the whole thing. Okay. So, Gz is equal to, this is the final expression, you have to remember this for this course, that is what I am saying. But the other things you have to remember forever, like Gz is equal to Gm sin phi is something you have to remember forever, all your career you will remember that, and this for the timing you have to remember it. Okay. All right, thank you.